Yeah, good morning to one and all. For continuation of the last class, we are discussing about the energy methods. So once the unit load method is being completed and thoroughly understood by you, and now today I would like to start the new method, that is Maxwell's law of reciprocal deflection. See, these all methods they proposed to calculate the deflections only, but the different way of approaches by different people, that is Maxwell's law of reciprocal deflection. In the method itself he has been mentioned clearly that what is meant by reciprocal. Reciprocal means reverse way actually. So you can have a one like random diagram over here having the support conditions of hinge and roller there, and there are 2 points A, I and J. Say if I wanted to calculate the deflection at I and J, what is the methodology or quotation I have to follow. That in any elastic structure the displacement at point J due to unload at I is equal to deflection at I due to unit load at J, that is delta Ji equals to delta Ij. So note, Maxwell's law is valid for both prismatic and non-prismatic structures. Maxwell's law is independent of cross sections, and delta BC equals to delta, and delta CB equals to delta, and delta CB equals to delta by 2. So then there is a understanding about the work. Work has been divided into real work as well as virtual work actually. Then if you see the work done by W1 in the direction of I itself, and deflection in same direction equals to W1 into delta 11. Then virtual work done by a load due to the deflection caused by some other load is called virtual work or imaginary work. Virtual work equals to W2 into delta 12. Then you can continue this one. Then in virtual work either force is small or displacement is small. In solid mechanics displacements are small because it's a virtual actually. In fluid mechanics force are virtual, and there is another method. Once this Maxwell reciprocal method is completed, there is Maxwell and Bette's proposed one more theorem actually, that is Maxwell's Bette's theorem. Virtual work done by P system of loads due to the displacement caused by Q system. Then that means if I apply the load at P, then I can measure the deflection at Q actually. So in that way, that is equals to P1 into delta 1 Q and P2 into delta 2 Q actually. That is virtual work done by Q system, Q1 delta 1 P plus Q2 delta 2 P actually. That means according to Maxwell's Betty, these two virtual works are equal. Then another very interesting method is Castigliono's minimum strain energy theorem. Every system in this universe will reach its stable equilibrium if it has minimum energy. This is the basis for minimum strain energy theory. In any and every system of statical indetermination wherein a number of different values of redundant forces satisfy the conditions of statical equilibrium, their actual values are those that render the strain energy stored to a minimum. Dou u by dou r equals to 0, dou square u by dou r square equals to positive. In two hinged arches, dou u by dou h equals to 0, our total strain energy stored in is minimum. So that is all about your Castigliono's theorem. You can see here that is general understanding about the like types of statically indeterminate beams. The number of reactions in excess of the number of equilibrium equations is called the degree of static indeterminacy. These are the best examples to know about the statically indeterminate structure beams actually. Then you see here analysis of the by the differential equations of the deflection curve. That is, if I do one time, that means dx by dy, otherwise dy by dx, y equals to basically deflection, whereas dy by dx equals to slope. D square y by dx square is the bending moment, and d to the power of q by y by dx cube is the d cube y by dx cube is the shear force, and whereas the d to the power of 4 y by dx to the power of 4 equals to load. Then that is derivative part I am talking about. When you do the reverse way in the integration part, the procedure is essential. Sorry. The procedure is essential, the same as that for a statically determined beam, and consists of writing the differential equation, integrating to obtain its general solution, and then applying boundary and other conditions to evaluate the unknown quantities. The unknowns consists of the redundant reactions as well as the constants of integration. This method have the computational difficulties that arise when a large number of constants to be evaluated. It is practical only for relatively simple case. Then a proper cantilever beam AB supports a uniform load Q. Determine the reactions, shear forces, bending moments, slopes and deflections. Choose RB as the redundant. Then RA equals to QL minus RB. MA equals to QL square minus RB into L. And the bending moment of the beam is M equals to R into X minus MA minus QX square by 2, whereas QLX minus RBX minus QL square by 2 minus RB into L minus QX square by 2. Therefore, EI shear one time movement equals to QLX minus RBX minus RBX minus QL square by 2 minus RB into L minus QX square by 2. Then shear force equals to that means not shear force, I think slope QLX square by 2 RB into X square by 2 and QLX square by 2 minus RB into LX minus QX cube by 3 plus C1. Then EIB that is equals to QLX cube by 6 RB into X cube by 6 QL square into X square by 4 RB LX square by 2 C1X QX to the power 4 then boundary conditions V of 0 equals to 0, V dash of 0 equals to 0, V of L equals to 0. It is C1 plus C2 equals to 0 and RB equals to 3QL by 3, 3QL by 8. RA equals to 5QL by 8 and MA equals to QL square by 8 actually. Timer. The shear force and the bending moments are given like this. Then you see here that is RA equals to QL minus RB, MA equals to QL square by 2 minus RBL, and the bending moment of the beam is M into RAX minus MA minus QX square by 2 and QLX minus RBX minus QL square by 2. Cut. Then V double dash equals to MU M that is equal to QLX minus RBX minus QL square by 2 RBL minus QX square by 2. Then EI V dash equals to QLX square by 2 RBX square by 2 QL square QLX QL square X by 2 RBLX minus QX cube by X 6 plus C1. Then EIV equals to QLX cube by 6 and RBLX cube by 6 and QL square X square by 4 and RBLX square by 2 plus C1X QX cubed for a 4 by 24 plus C2. And boundary conditions are V of 0 equals to 0, V dash of 0 equals to 0 and V of L equals to 0, and it is obtained C1, C2 are zeros. RB equals to 3QL by 8 and RA equals to 5QL by 8 and MA equals to QL square by 8. So likewise we can calculate the values and things for given numerical actually. The shear force and bending moments are given like this. That's all. So with that note, I would like to stop the today's class um, with the completion of almost CO1 syllabus. Actually, as of now in CO1 syllabus, I have been covered the first moment area method, conjugate beam method, unit load method, then energy theorems thoroughly has been discussed. In the energy theorems, strain energy theorems like Maxwell's reciprocal theorem, Betti's laws, Cauchy-Reynolds theorems 1 and 2. These all theorems has been discussed. So this is only the basic syllabus we have to cover in the overall CO1 content actually. So in the next class I am going to cover the CO2 syllabus. So that is propped cantilever as well as fixed beams, analysis of propped cantilever and fixed beams actually. Thank you one and all.